Swayam Prabha. Digital India. Educated India.
We continue looking at non-renewable resource economics, and in the previous module we have looked at a situation where there is perfect competition, and we found out what is the optimal strategy for the mine manager. We found out what is the price trajectory, we found out how much quantity would be taken in different years and the time for which the resource will last. In this condition, what happens is the demand or the inverse demand curve is given, and any company or an owner of a mine has no way of influencing that demand. Let us now look at the question, what happens if all the mines are controlled by one company or one individual? That means, what happens if there is a monopoly? And of course, as you would expect, the rules would be changed, because then the monopolist can actually influence the total quantity which is being released, and because the total quantity being released is being influenced, the price would change. And so the monopolist has a way to dictate a price and can then decide. So in this case, the optimization changes. The monopolist tries to maximize the revenue, and this in a similar fashion like the analysis we have done in the last section, where we said that the costs are constant and we can take the price minus the cost, or we can neglect the cost. So the revenue that we will have R T will be P T into Q T. Now, in actual practice, we have seen this case of a monopolist affecting the prices. In some cases, it may be one individual which is a monopoly, or it could be a cartel of producers. For instance, OPEC is a cartel of oil producing and exporting countries, and in the 1970s, OPEC decided that it was going to control the quantity of oil that it was going to release. And with the result, you could see a sudden spurt in the oil prices. This is called the oil shock, and that is the point at which all countries started looking at energy independence and looking at energy efficiency, and this was the start of the whole movement to look at energy conservation and energy efficiency. So we would like to now look at from a monopolist point of view. If you have the revenue and we want to maximize the discounted sum of the revenue R T by 1 plus D raised to T, T is equal to 0 to T. So it is very similar to the earlier situation that we had. Only thing is that in the case of R T, the monopolist is able to influence the quantity that is being released overall, and hence is also able to influence the price. And this will be subject to the constraint that sigma Q T, T is equal to 0 to T, is equal to the total reserve that we had, which is R 0. So when we take this, we can take the Lagrangian, which will be very similar to the last analysis that we did, but R 0 minus sigma T is equal to 0 to T Q T, okay. And this Lagrangian divided by the differentiated with respect to del qt, set this equal to 0, what we get is we will get the we are differentiating the total revenue that we have with respect to qt. So, what we will get is the marginal revenue. We can differentiate this and we will get delta RT by del qt 1 plus d raised to t minus lambda is equal to 0. So, essentially what we get is delta R t by del q t is also known as the marginal revenue. That means, the revenue per unit of q, and what we would get then is that the lambda value is going to be equal to marginal revenue divided by 1 plus d raised to t. So, this is that in each time interval, just like we had in the earlier case, we had the price increasing at the discount rate. Now, we are having the marginal revenue 1 by 1 plus d and so on, marginal revenue t by 1 plus d raised to t. Now, let us take a situation where we have a linear inverse demand curve. So, we have P t is A minus B q t. So, then R t becomes A q t minus B q t squared, right. So, del R t by del q t is A minus 2 B q t. So, once we plug this in, the value of lambda which we get is A minus 2 B q t by 1 plus d raised to t. And we said that MRT increases. So, MR marginal revenue in time horizon t will be equal to marginal revenue in 0 first year into 1 plus d raised to t. Now, let us consider the linear inverse demand curve and take the situation when the resource is completely exhausted. When the resource is completely exhausted, at that point q t capital T will be equal to 0. At this point, what will be happening will be the marginal revenue which we have must equal to the price per unit, that will be equal to the price, and that is when the monopolist will not want to produce any more. The marginal revenue will be equal to the price, and that is equal to, we said, A minus B q t. So, this is going to be equal to A. So, A is going to be equal to M R 0 1 plus d raised to t, and then we can substitute this in this expression. So, that we get M R t is equal to, this is capital T when it gets exhausted, capital T. This is going to be A by 1 plus d raised to capital T multiplied by 1 plus d. So, this is marginal revenue is going to be 1 plus d raised to t minus t, and we have already derived that the marginal revenue for the linear inverse demand curve case is A minus 2 B q t. So, we can put this as A minus, we can equate these two terms. BQT is A 1 plus D raised to T minus T. We can now get from this, we can put this as 2 BQT is equal to A into 1 minus. So, looks very similar to the competition case, but with a difference. We have now, this is QT is A by 2B into 1 minus 1 plus D raised to T minus T. If you remember, you can look back at the earlier derivation that we had done. In the case of this is for the monopoly, and for perfect competition, for a competitive market, we got QT is equal to A by B So, if you look at this, of course, in the case of the monopoly, the value of exhaustion, the number of years T would be different, but in general what you would find is that the monopolist would in a particular year release less amount of Q, so that the price increases and the overall revenue increases, with the result that, as we would expect, the resource is going to last for a longer period under a monopolist case. So, if we look at this, we would expect qualitatively a curve like this, where you have QT and T. This is for, if this is the shape or competitive market, then the monopolist would be, this is how the monopoly would look like. So, you can look at the book by Conrad on non-renewable resource, on resource economics, and there is a chapter on non-renewable resource economics which shows some of these. If we then take this, the same thing, you can see the this is the actual this is for a this is a plot which is shown from Conrad, which shows a similar kind of trend for a particular example. So, now what we would like to do is we would like to look at this, take that expression, and just like we did for the competition case, we would like to derive how much time the resource is going to last for. So, in a similar fashion, we take T is equal to 0 to T minus 1. Remember that in the last year, Q capital T is equal to 0. So, that need not be added. Q T will be equal to 0 to T minus 1 A by 2B into 1 minus one plus D raised to and if we use this in the same fashion as we did derived for the competition case, this becomes a geometric progression, and finally we get an expression which is like we get 2B R0, this sum will be equal to R0. So, 2B R0 by A is T minus 1 by D 1 minus 1 plus D raised to T. and the final expression that we get is T is equal to 2 B R 0 by A plus 1 by D 1 minus 1 plus D raised to T. This is for the time for the monopoly. And you would remember that we have a similar expression when we had the competition, and only difference was that in this case this was BR 0 by A, and so what you would find is that the time taken would increase. And now the question is, of course, does that mean that a monopoly is better from a resource point of view? From a resource point of view, the monopolist conserves the resource, because the monopolist is looking at the overall maximization of revenue. But in the process, given the discount rate that is there, the population and the consumers are exposed to much higher prices, and because of that the overall utility of society is less under a monopolist case, even though the resources get conserved for a longer time. So now let's do one thing. Let's take the same whatever we have learned for competition and for monopoly. Let us now solve one particular example, a numerical, which is there in your tutorial sheet. I will just show you this number, and this is the tutorial sheet. This shows that we have a tutorial problem. The inverse demand function for a fossil fuel is given to you as Pt is equal to 1 minus 0.1 Qt, right, which means that A is equal to 1, B is equal to 0.1, and we have also the value of discount rate. R0 is given to you as 75, R0 is 75, and D is 5%, which is nothing but 0.05. Okay. So, the first part of the question is, what is the price of elasticity of demand for this function when Qt is equal to 5 units. So, when Qt is equal to 5, let us just substitute Qt is equal to 5. So, what is the value of Pt? It's just 1 minus 0.1 into 5, this is 0.5. So, the answer is 0.5. So, the differentiate this del Pt by del Qt, this is minus 1. So, if we look at the elasticity, that is going to be del Qt by del Pt into Pt by Qt, which is, this is del Qt by del Pt, this is 1 by minus 0.1, Pt we said is 0.5, and Qt is 5. So, you will find that the elasticity is minus 1, which implies that if we have a 1% increase in the price, there will be a 1% decrease in the quantity, and that is the elasticity. So, we have solved the first part of the question. The second part, B, says determine the time value of extraction for a mining industry under pure competition. So, when we talk about solving this for pure competition, we will have this as, we have Pt will be, for pure competition, this will be P T into 1 plus D raised to T. So, 1 point D is 0.05, 1.05 T. Now, we know at T is equal to T, Qt is equal to 0 and Pt is equal to A, which is 1. So, 1 is equal to P0 1.05 raised to t. We can substitute for P0, so that we get Pt is equal to 1.05 raised to t minus t. So, you remember the formula that we had derived for the time that this will last. We want to, this is the only unknown is capital T. We need to determine capital T, then we can plug it back and we can get the equations for Pt and Qt, in which case we would determine the time path of extraction. So, once we do this, we check Br0 by A plus 1 by D into 1 minus 1 plus D raised to T. Just substitute the values. This is going to be 0.1 into 75 by 1 plus 1 by 0.05 into 1 minus 1 by 1.05 raised to t. So, if we simplify this, we will get t is equal to 7.5 plus 20 into 1 minus 1 by 1.05 raised to t. Now, when we look at this, we will, this is, as we said, this is an equation where we have to iteratively solve for t. So, let us assume a certain value of t. Let us say, suppose t is equal to 10 years. We can substitute t and get t is equal to 7.5 plus 20 into 1 minus 1 by 0.05 raised to 10. You can plug in these values and you will see you get t comes out to be 15.2. Now, we take 15.2 as a starting point and solve to get the next value of t, and then you get t is equal to 18.0, and then the next iteration we get 19.2. You can solve this and check 19.7, 19.8, and it converges to about 19. You get t approximately 19.94. We can round this off to about 20 years. So, we have solved this part C. When does the resource get exhausted? The resource gets exhausted at 20 years. And then what happens is that if we now substitute back, we get that Pt, which we had already solved. We got this as Pt is equal to 1.05 into t divided by 1.05 raised to 20, right. And if you see this value of 1.05 raised to 20 turns out so you can get this. So, we got an expression for Pt. We also now can substitute this and get the expression for Qt, and with that we get essentially the value of Qt in different years. Now, let us look at, for the same situation, the part D. Would the time path of extraction, so once we have this, we can plot it for different years, and we have got the plot of Pt versus time and Qt versus time. Now, the question is, would the time path of extraction for a monopolistic mining industry be different? And so, if you look at this, as we have seen earlier, what happens in a monopoly is that you are able to affect the quantity supplied and hence the price, and because of that you release less than in perfect competition. It's better for you to have less quantity mined, and with the result that we expect it to last longer. If we take this, if you remember, we had derived now for the monopolist that this is going to be 2 Br0 by A plus 1 by D 1 minus 1 plus D raised to T. More or less things, the equation looks very similar, except instead of 7.5 this is now 15. So, once we do this, we will get obviously a different converged solution. So, if we start with t is equal to 10, you will get t is equal to 15 plus 20 into 1 minus 1.05 raised to 10, and you get the next value becomes t is equal to 22.7, and as we go ahead you will find that it converges to about 30.5 years. So, t approximately 31 years. In the first case we found t is 20 years, and in this case it is 31 years. So, qualitatively we realize that essentially the monopolist wants to maximize revenue, and because of that we produce less from the mine in the initial years as compared to the competition case, and with the result that overall the revenue increases. Now, the question is that what happens, we also saw repeat this with d is equal to 10%. If the discount rate is higher, what would happen? If the discount rate is higher, it means that we are counting future cash flows and discounting it by a larger amount. So, we would prefer to have a profit or a revenue today as compared to in the future, with the result that what would happen is that we would actually mine QT at the initial periods would be higher, and then the mine would get exhausted in a shorter time period. You can repeat this on your own and cross check. So, with this we have completed the portion on non-renewable resource economics. We have of course done this with a simplistic set of assumptions. You can relax all of these assumptions. You could have a situation where the costs of extraction change. You could have a situation where there are different kinds of demand, inverse demand curves, and but this gives us a way in which from first principles we can identify how an optimal mine manager would think and what is the way in which the resources would be used, subject to the fact that of course the total amount of resources are finite.